Let's talk about switches, basic electrical switches. What could be simpler, right? Here's a small sample of some fairly common types of switches. Here's a very familiar item, your basic light switch or wall switch, some limit switches or detect switches, usually manually operated rocker switch. Here's a reed switch, which is operated by a magnet. Dip switch here is often used to select or deselect options on a circuit board in a computer or some other device like that. Later in the video, I want to talk about misapplication of one of these switches. At the heart of it, all these switches are about metal-to-metal contact. Here's a very simple momentary switch. Not very convenient, but just bare wire contact. Metal to metal, making and breaking a circuit. Let's just take a quick look at a few of these switches. Okay, here's a common wall switch or light switch. Throw the lever and inside a couple of metal contacts are brought together to make the circuit. Throw it the other way, they're moved apart to break the circuit. And all the different switches I've shown here are designed for different purposes, but they all have that metal-to-metal contact at the core of their function. Here's a manually operated rocker switch. Here's a fairly common type of limit switch used to make or break a circuit when something mechanical moves into or out of position. This one has normally open contacts, which are wired up now. Normally closed contacts, which basically reverses the function of the switch. It gives the designer a couple of options. Here's a reed switch that's operated by a magnet. This one is a little larger than most reed switches. I bought it so that I could easily see the contacts. There are a couple of metal leaf springs in there with contact material, contact plating, and when there's a strong enough magnetic field concentrated in the ferromagnetic leaves, they attract each other and move together, and the contacts touch each other, making the circuit. Here's a dip switch that's an assembly with several switches in it, 4 in this case. Here we'll just show the basic switch function, on and off. Here's a small detect switch. Note the rating is only 1 milliamps at a fairly low voltage. I am not going to hook this up to my light, which consumes about 300 milliamps, because I don't want to burn up the switch. So you'll notice that these switches have different ratings, and most of them have data sheets that spell out a lot of their operating characteristics. The most important ratings for a switch are usually the operating current and voltage. And most of the time, you just want to select a switch that can handle at least as much current as you're going to demand of it, and that can interrupt a high enough voltage for your application. But there's a little known fact about switches. Hopefully most electrical engineers designing hardware are aware of this. There are cases where a switch used to control a very small current, well below its rating, may not be suitable for such an application. And I'm going to show you an application where this particular rocker switch was misapplied. This is a nice general purpose switch. It can handle a lot of current and a wide range of voltages, but it's not suitable for switching very small currents. And the reason is the contacts over time will oxidize. They'll form a little film of oxide on the surface of the contact material that acts as an insulator. But a lot of these switches that are used to make and break circuits that carry a significant amount of current rely on the arcing that occurs during those switching operations to help clean away the surface oxides. Probably most of the basic electrical switches you'll come across are in that category. So this switch is not suitable for interrupting small currents like you might use as a signal to a microprocessor. One thing you can do in a case like that is use a different type of switch. Here's a detect switch that's designed to operate at low voltages and low currents. Whereas the contact plating in this switch may be silver or tin, or silver tin oxide, or so on and so forth. The contact plating in a switch like this is typically going to be gold, at least on one side. It's really best to have gold plating on both sides. So let me show you where this switch was misapplied. Here's a picture of one of my recent purchases. This is a Ryobi 40 volt cordless mower, and I've bought 4 of these mowers over the years, starting with a much older model, and I really like these mowers. But you know, in a sense, I can predict the future, because I know that in a couple of years I'm going to be replacing some of these switches. The mower has several interlock switches, things like detecting that the handle's fully extended before allowing the blade to spin, or making sure that there's a grass deflector or bag in position, or requiring you to hold a safety bale down while you mow so the blade will keep turning, or requiring you to press a button to operate one momentary switch and then pull the bale in to actually start the blade. Both of those last 2 switches I just mentioned are the same type of switch. It's a very nice switch. All the switches I've shown you are high quality switches, but this one should not be used in this application. I know from painful experience that in a couple of years this mower is going to do what all the older ones that I have done. It's going to begin to operate intermittently. I'll start the blades and I'll start mowing, and after a few minutes of operation the blades stop for no apparent reason. I can start them again, mow for a few minutes, and repeat that cycle until I go crazy. The engineers at Ryobi are probably well aware of this problem. I expect they have a team of engineers with a lot more combined experience in electrical and mechanical and product design than I have. Those electrical engineers on the team are no dummies. They're probably well aware that these switches will not be reliable after a couple of years of operation out in the real world. They had choices. They could have spent a little bit more money, and we're probably talking about pennies or maybe dimes per unit. They could have used a switch with gold-plated contacts. There's actually a very minute quantity of gold in a switch like that, but of course you will pay for it. They could have used a solid-state switch like this magnetoresistive sensor here, and sense the presence of a magnet. I'd like to think that if I had been on that design team, I would not have signed off on the selection of a switch like this to control that low current signal. But of course, it's also probably true I would have been overruled at some point by some salesperson or manager. That's the way it goes. Oh, and don't take my word for it on the dry contact or low current switching. Let me just direct you to a very nice book, The Art of Electronics by Paul Horowitz and Winfield Hill. I've got the 3rd edition, and on page 58, section E, it says, "It's always okay to operate a switch below its maximum ratings, with one notable exception. Since many switches rely on substantial current flow to clean away contact oxides, it's important to use a switch that is designed for dry switching when switching low-level signals. Otherwise, you'll get noisy and intermittent operation." As the Ryobi engineers are no doubt aware. But that's enough about switches for now.